started.
I'm ready whenever you are.
All right, well, good morning, everybody. Thank you all for coming. I'm David Murphy. I'm an assistant professor in mechanical engineering in the College of Engineering up at Tampa, and I'm serving as the outside chair today for Mary's defense. So with that, I'd just like to introduce the committee. We have Dr. Paul Rhodes, Dr. Kendra Daly, Dr. Al Hine, Dr. Robin Economy, Dr. Anna Arellano, and Dr. Mark Luther. So with that, I'd like to introduce Dr. Paula Rhodes.
Thank you. Thanks for serving as her chair. We really appreciate it.
Especially coming over in traffic.
Yeah.
Yeah. So I'm probably going to cry, just to let you know. She's my
Don't
last
do
student.
that.
It's going to be some
I will.
crying today. This is what happens when you have lots of women around. I'm so proud of Mary to finish. Mary came to us from geology. She has a bachelor's and a master's degree in geology from Rensselaer Polytech. She came to us in 2000?
2010.
2010, yeah.
It hasn't been that long. It's long, but not that long.
At the same time that her youngest daughter went off to college. And she's been teaching for the last 4 years. 5 years. I didn't bring my computer, so I didn't have her bio with me, and she provided me a little sketch, but she left out the dates, which is, at our age, is a good thing.
Yeah.
So she's been teaching for the last 5 years at Florida Gulf Coast University in the Marine Science Department. And I'm so proud that she finished because it was kind of a race between Mary finishing and some of her committee members being sent off to the old folks' home. So this is a really exciting day that we made it.
Yeah.
We're all here.
Yeah.
And now I'll give you Mary.
Thank you. Well, thank you to all of you for being here. The committee, of course, and all of the colleagues that I've had at the College of Marine Science, and Dean Jackie Dixon, who couldn't be here. It was just an honor and a pleasure to be able to work with all of you. So I'm going to take you through a little walk back in time to look at how we can use fluorescence to investigate petroleum in the marine environment. So I'll just give you a really brief introduction into petroleum, especially in the Deepwater Horizon oil spill, which is when I started my work, so now you know how long it's been. A little bit about fluorescence, just so that you understand why it's a beneficial analysis method to look at petroleum. The specific research questions that I looked at, and there were 3 major projects that I did, just a little bit about methodology, and then a summary of the most important results. There are many more results, but I'll just stick to the ones that I think are really exciting and interesting to share. So you've probably seen this picture many, many times, although it's kind of fading into memory now. Kind of hard to believe. It's coming up on the 10th anniversary next April of the Deepwater Horizon oil spill, excuse me, in the Gulf of Mexico. There were a lot of groundbreaking things about this oil spill, the depth of the wellhead, excuse me, that the oil continued to flow for 87 days before they were finally able to cap the wellhead. And there's some question about that, which I'll get to later. And then the use of dispersants to try and combat the impact of the oil on the marine environment. So here we've got a photo which was taken on an ROV called the Scandi Neptune, and you can see the stream of dispersants being injected, corrects at 9,500, right into the wellhead plume. And then we also did have dispersants applied to visible oil slicks at the surface, which is the traditional way that the SMART protocol calls for the application of dispersant to be used to fight an oil spill. So After any oil spill happens, the Deepwater Horizon was not unique in this way. The the oil will be dispersed physically at first by wind and currents, and it starts to weather. So the operations that are included are in the order of, pushed the wrong button. In the order of occurrence, starting with evaporation as the volatile components of the oil make their way to the surface into the atmosphere. BTECs and the lighter PAHs will be the first ones to evade into the atmosphere. Then the oil that is left at the surface will begin to emulsify and forms a mousse type of a compound. It can also dissolve into the water column. Oxidation is involved both in the water column and in the creation of the mousse. Obviously, it's going to be transported by the wind and the currents horizontally as well as vertically. And then we get fallout to the benthos as well as shoreline stranding and eventually tar balls, which can be found wherever the water gets stranded on the shore. The persistence can range from an amount of days to years, which is something that we have seen with the evolution of the Deepwater Horizon oil spill. So now we'll move into fluorescence. This plot shows the wavelength in nanometers of incoming light energy or photons. The substance, any substance that's capable of absorbing light energy, possibly can also emit at a longer wavelength. And the reason for the emission at a longer wavelength is that it gets converted internally within the structure of the molecule. Essentially, the photons that are incoming excite the electron field, especially in the pi bonding in aromatic molecules. And then as that energy needs to dissipate, it gets converted to a longer wavelength as some energy is lost through heat or through internal conversion. So that's why there's always a wavelength change here between blue light and green light, but it can also happen in the UV to a higher wavelength. So this on the y-axis is the measurement of the fluorescence intensity, just normalized to 1. So if we take a number of these excitation and emission scans and put them together, we get something that's known as an EAM. And collectively, we call this excitation emission matrix spectroscopy. So you'll notice that there are many, many individual lines here. Here's the excitation wavelengths. These are the emission wavelengths, and you'll note that the excitation ends at 450, where the emission goes up to 700 to account for that Stokes shift. These are in quinine sulfate units. And I should have pointed out that this is the absorption and emission spectrum for quinine sulfate. This is a typical unit for fluorescence spectroscopy because of the very reliable absorbance and emission that quinine sulfate dihydrate exhibits in solution. So it's quite common to put your results into quinine sulfate equivalent units. And you can see here on the x-axis, that's what we have in this image. These are the recognized fluorescence spectra in the aqueous environment. So we've got here peak A and peak C, which are characteristic of humics that are present in the marine environment. Peak M, which is more characteristic of the marine environment, and it's hypothesized that that's due to microbial action. Peak B is characteristic of proteins, which would be present in the marine environment from breakdown products of any organisms, from microorganisms on up. Peak P is pigment, and this is typical of chlorophyll, the excitation emission of chlorophyll. So this is just putting that into a flat contour plot, kind of looking at it like a map. So, you know, if you're familiar with hiking, this would be one peak, this would be another peak, and this is the same nomenclature that you saw in the previous EAM. The nomenclature has evolved a little bit. You'll see that there are corresponding A sub B to the B peak, A sub T to the T peak, and so on, because many compounds actually have two excitation emission peaks, and the lower wavelength one is given the subscript nomenclature. We're going to be talking about petroleum, and you might wonder, well, where does petroleum fit in all of this? These two peaks are characteristic of proteins, tyrosine and tryptophan specifically, that would be present in the marine environment. It turns out that the excitation emission peak for petroleum that we discovered lies right in between them, and it's the wavelength pair that's characteristic for naphthalene, a two-ring hydrocarbon. So this is a table that just puts all of what I just said into perspective. You can see all of those peaks that were shown in the previous image, as well as the excitation emission pairs for the fluorescent components of petroleum from benzene, which is part of the B-tex, that is very volatile and evades quite quickly. You can see that that's got a very low excitation and emission. Then moving on up, naphthalene, anthracene, and pyrene. And as you go up in number of aromatic rings, the proportion that's present in any crude oil is going to decrease. So it's quite common for the naphthalene to be the most prevalent. And you can see here, we do have two peaks at an emission of 320 to 322 and an emission of 334. So I'm going to ask you to just mentally make a note of that as we go forward to look at our results. Traditional petroleum analysis has involved extracting into a liquid such as dichloromethane, which is the liquid that is commonly used for GC and GC mass spec. Often it's then, and I should mention that this is a very time-consuming and chemical-heavy process. Then it's screened with gas chromatograph flame ionization detector and comprehensive analysis through mass spec. And there are further refinements that are now being pulled into the process, GC by GC, and methods of analysis that are even more instrument heavy and even more time consuming. Time to catch my breath. We can also use HPLC, and all of these methods are somewhat subjective as you're looking at the results and you need to pull information out of them, and very time consuming. They also involve instruments that are kind of difficult to take to see. When I was out on the Weatherbird 2, there was a researcher from the Hollander lab who had GC mass spec on the ship, and it wouldn't work because it was not happy about all of the pitching and rolling that was happening out there. So let's move on to why use fluorescence to look at petroleum. Really minimal sample prep. At most, you need to filter it through a glass filter, although I did not filter my samples because that actually wound up removing some of the oil signal because the oil would adsorb to the Wattman filters, and we didn't want to lose any signal. It only takes about 3 milliliters to fill a little quartz cuvette, so you don't need liters and liters that you would need for the extraction purposes. Very quick. The instrument that I used, the Hariba Aqualog, takes about 10 minutes to run a sample for a full EAM profile. We found that we could get down into the parts per billion range, and although we don't fully know the consequence to marine organisms, It has been noted that toxicity down to the parts per billion range is quite possible and probably likely. Really easy to use, portable. Anna and I carried it out and put it on the bench in the ship, just the two of us, which makes it easy to use. And you can also make use of in situ fluorometers, which I'll talk about in a minute. It can also be complementary to the GCFID detection. So there's a lot of words here. My research questions were to find out what the best excitation emission pair was to find oil in the natural environment. And I'm going to prove to you that the excitation emission pair of naphthalene turned out to be the best marker for that. To look at what the application of dispersant did to the fluorescence profile that we would find in a petroleum and water solution, to see if there were similarities and differences and what they were when we looked at different types of petroleum with different viscosities, with and without chemical dispersant, and to take a look at how the appearance of the oil spill looked over the year following the Deepwater Horizon oil spill. These are the two instruments, very similar. They both have a xenon lamp, which has the same excitation spectrum as natural sunlight. So it's applying the same photon strength that you would see from the sunlight. The excitation and emission information was very similar. The Fluoromax 4, which was the instrument I started with, has a photomultiplier tube detector, while the Horiba Aqualog has a CCD detector. Both very sensitive. I like the PMT a little bit better for the clarity of the results, but they're both very good instruments. And the Horiba Aqualog is capable of doing absorbance as well as excitation emission. So that's a really handy piece of information to have. Real quick schematic of how it works. You've got the light source. Monochromator narrows the wavelength of that beam. It goes through your cuvette. There's a reference channel that collects the amount of energy going in, and then your signal channel, which is collected at 90 degrees to the sample. For the Aqualog, the absorbance channel is collected straight through the sample. And that's what the Aqualog looks like. So now we're going to talk about the three different experimental series results, the most important ones. So now we're going to do this walk back in time. The Baffle Flask experimental series is actually the final research that I did here at USF. This was done in the lab with 25 different types of oil, which were provided to me by Bedford Institute of Oceanography. This was a joint program funded through the EPA and wound up becoming a report to BSEE for the United States government. I added the 25 different types of oil to artificial seawater so that I was eliminating competing signals from naturally present organic matter, and then added Corexit 9500. First I did it without dispersant, and then at the dispersant to oil ratio, that's what DOR stands for, of 1 to 200, 1 to 100, and 1 to 20. 1 to 20 is thought to be the target for dispersing oil in the natural environment. And I did 3 replicates, you can see here, on a shaker table in the hood, upstairs in the back of the MSL building, and analyzed them all within 5 minutes of the shaker table ending. So now we're going to take a look at what those results look like. And for comparison, this is a water sample that does not have any petroleum in it. It does have naturally present CDOM, and it's evidence of the Mississippi River plume. This was a sample that was collected aboard the RV Walton Smith and sent to the lab for analysis. Those researchers were looking for evidence of the Mississippi River plume traveling through the Florida Straits at the end of the summer in 2011. So we can see here the excitation wavelength and the emission wavelength. These are just machine units. It's not been put into quinine sulfate equivalents here, but you can see with an excitation of about 300 and an emission of about 400. This is a typical profile for naturally present marine or M-peak organic material. Now we'll take a look at what oil looks like. And I'm going to point out that the axes have changed here. And this is just the software that runs the instrument. This was collected with the Fluoramax 4. This was collected with the Aqualog for the baffle flask analysis. So you can see here that the excitation is on the x-axis, emission is on the y-axis. The first important result, for all 25 types of oil, there were 4 peaks that were present in all oil types to at least some degree. This is the most important one, that excitation in the low wavelength of about 225 and 320 to 325 is characteristic of naphthalene. And then we've got minor peaks, even lower in the UV. The lamp strength is not really strong at that low wavelength. So it's difficult to find this peak often in your analyses. We've got one here that is hiding behind the Rayleigh scatter. Rayleigh scatter is an inherent property where the incoming light molecules are scattered by water molecules, and it's just a blaze of energy. So it's common to just eliminate that because you can't get at the information that's behind that very high intensity energy, unfortunately. And then we've got a 4th peak, which is that double peak that I talked about with the naphthalene that was present to a greater or smaller degree. These units are in Raman units, which is what the community is moving toward. Rather than running a quinine sulfate series for concentration and then turning the units into quinine sulfate equivalents, we can do a scan of a water blank and just put everything into the units that the Raman scatter creates from the sample in the blank, and that can be done every day. Doing a dilution series with the quinine sulfite dihydrate is very time consuming. It's very particular. We can just run a blank at the beginning of every day in order to put things into Raman units. So the next result that we found is the change in the spectral characterization with the addition of dispersant. So here we've got MC252, which was collected from the Discoverer Enterprise right near the wellhead in July of 2010, without the addition of any dispersant. Then we add dispersant at a 1:100 ratio, and you can see how it extends and broadens the fluorescence into the longer wavelengths. And at full dispersion at 1:20, you've got a very clear and obvious peak, which could be used to tell people in the field whether your dispersant is really doing what you want it to do. The final result from the baffle flasks was the difference that was related to viscosity of different oils. So that allowed me to separate them into type 1 and type 2 oils. This is at that full 1:20 dispersion. And you can see the variation between Mesa, which is a South American crude oil, and Arabian Light. We also just looked at the Louisiana Sweet Crude, which is in this type 1 category, versus Santa Clara, which is a very high viscosity oil from offshore California, and fuel oil, which I found to be pretty anomalous. That was interesting looking at the fuel oils. So the conclusions that I came up with were that we could divide oils into those 2 categories Responders could decide whether or not to use dispersant because the type 2 oils, as you could see, didn't really respond really well to being dispersed. So you could forget about that if you had a type 2 oil. I've got the database of 25 oils, which I intend to share with the scientific community. Maybe can be useful in fingerprinting of oil sources in the future. And as I mentioned, this could be an important tool for responders in deciding how to remediate an oil spill. The next, going back in time, experimental series that I did was at the Bedford Institute of Oceanography in Halifax, Nova Scotia. This photo is taken by Jim Farr of NOAA, and we are standing by the side of the wave tank. That's me, one of my committee members who's being anonymous in this picture, and a number of other researchers from Canada and from literally across the US and in other countries who came to test in situ fluorometers. And you can see the computer array that's connected to the in situ fluorometers, which are down there in the wave tank. So it was held in June 2011 to investigate how well did all of these in situ fluorometers that researchers were putting on CTD rosettes when they went out in the year following the oil spill, how good did they do at detecting oil? They were, the researchers were saying, well, we see something. Were they seeing oil, or were they seeing CDOM, colored dissolved organic matter, which is what the in situ fluorometers were really designed to do. So we put the wave tank in flow-through mode, so the water came in and was filtered as it came in from Halifax Harbor, and then exited after it was put through absorbent material to take the oil out of it. We tested the MC252 oil with Corexit 9500A at a DOR of 1 to 25, which again is in that range that people were looking for in the field for full dispersant efficiency. The final concentration of the oil, or the oil plus dispersant, was about 7 parts per million in the tank, and we took samples from the side port of the wave tank at these discrete time periods up to the 90-minute end of the experimental series. We did a total of 142 samples, some weathered, some fresh, some with dispersant, some without dispersant. These were the instruments that were in that wave tank, and then I analyzed my samples on the Hariba Aqualog. The BIO lab also analyzed them on a Shimadzu so that we could compare the results, what EAMS looked like from 2 different instruments, and again to try and get at what the excitation emission target should be, where that peak was that showed us we've got oil. So here's an example of what one experiment looked like. This was on the morning of June 5th. This is oil with dispersant. The wave generator was back at this end of the tank. They were paddles that got the waves going, as you would see breaking at sea. And then this mixture of oil and seawater was poured into the top of the wave tank. The wave tank now has actually been altered so that that can be injected down near the bottom of the tank, but this is the way that dispersed oil would appear on the surface at sea.
Talk about the natural seawater.
This on the bottom, thank you, is what natural seawater looks like. This is the appearance of CDOM. It's a yellowish green color. Excitation with blue light results in fluorescence in the green wavelengths. So this is what the natural seawater would look like before the addition of oil with dispersant. And this is actually one of the tiers of the SMART protocol, is to look for that consistency and color to determine whether dispersion is happening before you look at it with a fluorometer. Just for comparison, again, we've got, this is what the CDOM in the water would look like. Here we've got oil without dispersant mixed into seawater, poured on the surface, and you get that rainbow sheen that we've all seen in the parking lot when our oil tank is leaking. but you don't get that cloud of kind of rusty brown, and you could actually see globs of oil forming on the surface in the 90 minutes of the wave tank test. So here are the results from the wave tank tests. These symbols are specific in situ instruments which were used in the field in the response in the Gulf of Mexico. Two fluorometers that were manufactured by Chelsea in the UK, which they call Aquatracas, at 2 different wavelength pairs. They say one is for crude oil and one is for refined oil. The Turner Cyclops and the Wet Labs Eco are traditional CDOM in situ fluorometers, which people used and got responses. So we wanted to see, well, what were they seeing? And you could see that the Chelsea is at or close to the F max that I found in the baffle flask tests. You can also see the peak here that's very difficult for determination. But the CDOM fluorometers are picking up the kind of longer wavelength fluorescence, so we can be assured that the in situ fluorometers that were used were actually seeing oil. They weren't just looking at CDOM. And then we also compared the fluorescence results with chemical analysis. This was done by the people at BIO in their lab. They used an Agilent instrument to do GC mass spec. And I know that these are really messy looking plots, so I'll just tell you briefly what they are. This is BTEX, benzene, toluene, ethylbenzene, and xylene. These are the compounds that are very volatile and would evade through the atmosphere very quickly. And on the y-axis, we've got the fluorescence at 280, 340, which is close to that naphthalene peak. On this side, we've got the units in quinine sulfate equivalents for the experiments that were with Corexit. And on the opposite second axis, you can see the units are about half in quinine sulfate equivalents for the experiments without oil. So that shows right away that the fluorescence increases greatly with the addition of Corexit, but we can put them all on one plot and we can see that the correlation between BTEX, this is a fresh oil with dispersant, this is a weathered oil where nitrogen was bubbled through the oil to reduce it by about 7%, trying to make an equivalent of what would happen in the water column. And this is the fresh oil without dispersant. So we can see in both cases that there's a really good correlation between chemistry and fluorescence, and we would expect that. It's better with dispersed oil than it is with oil without dispersant. But the fact of the matter is fluorescent arises from the chemical structure of petroleum. It's a really complex chemical structure, but we should be able to draw a comparison between the chemistry and the fluorescence for that reason. So the results from this were we confirmed that those in situ instruments were actually seeing oil. This was published in ES&T with Robin Conmee as the lead author in 2014. We confirmed that the sensitivity of fluorometers could get down to the parts per billion range. As I said earlier, the final concentration was about 7 parts per billion in the wave tank. And I confirmed that that oil F max was in the naphthalene excitation emission range. So now we go back to the very beginning. And the response to the Deepwater Horizon. There I am using the Fluoromax 4 on the Weatherbird 2. You can see I'm holding a cuvette, that's the sample size. And as I said, there was no sample prep needed because we didn't want to get rid of any of the oil signal. The objectives were to look for the depth distribution. Could we see signs of petroleum in those subsurface plumes that now we have a lot of scientific literature that is pointing to the presence of those? And look for persistence. I went out on 3 research cruises myself in December of 2010, and then in February and May of 2011. There's also some research from August of 2010 while I was making my way down here to USF. So the collection was through Niskin bottles on the CTD rosette. As we were doing the downcast, there were specific depths that the Niskin bottles would be triggered, and we would also be looking at the in situ fluorometer results as the CTD was going down. And if we saw something interesting on the fluorometer or in the oxygen, dissolved oxygen reading, we would ask for the bottle to be triggered at that depth. We followed the protocol that was developed by the Coble lab in the years before I arrived. We tried acidifying the samples at first with 1 molar hydrochloric acid to shut down any biological activity. We tested freezing versus acidification to see what the effect would be on the fluorescence signal. And as I mentioned, we decided to do away with the filtering after the first cruise and seeing the difference that it made to filter the samples versus not filtering. Briefly, we found the less you do to treat the samples and the quicker you run them, the better your results are. So being able to have this instrument in the field and do an analysis in 10 minutes was a wonderful thing to be able to do. So in addition to all of the hundreds of samples that I collected on those 3 cruises, I also analyzed samples from the Nancy Foster, which were collected for us and sent to us to analyze in the lab. I did some sample analysis on the bellows to test those storage methods and to look at the background along the West Florida shelf. On the Walton Smith, as I showed you, the one example of evidence of the Mississippi River plume, and then some samples that were sent to us from the Okeanos Explorer to look for evidence from seeps to see if that might play a role in the fluorescence we were seeing. So these are the results from the Nancy Foster samples, and these EAMs were done in the Coble lab. I did not do these myself, but I wanted to show you because these are the earliest samples. This is a depth profile from a publication by Smith and colleagues that shows that fluorescence spike and oxygen anomaly that was characteristic of what we now know was a subsurface plume at about 1,100 meters that many researchers have pointed to. And these are the EAMs, which were done in MATLAB, that go with the samples first that was collected at 1,100 meters. And there you can see that naphthalene signature along with CDOM signature. This sample is the one that was collected at the surface. So you can see the difference between normal seawater, and I'll point out that these are in quinine sulfate equivalent units. You can see the maximum that we ever found was about 25 quinine sulfate equivalent units at the highest of all of the samples that we saw. So the samples that I wanted to focus on were the ones that I had a time series that went through all 3 of the cruises. And due to bad weather or different things that impacted the cruise plan, we didn't get to all of the sites in all of the cruises. The 2 that we did get to on every cruise were DSH-10, DSH-8, PCB-06, I looked at just to see the contrast going up onto the shelf a little bit, but we only had results from December and February, none from May for that particular site. This map was done by Kate Dubickus, and Kendra Daly shared it with me. You can see this is the area of interest. Zooming in, we look at the depth contours, and days of oiling came from the NOAA website. And this was data that was collected and shared by NOAA. So you can see that these 2 sites were in the range where there was really high oiling. This was from August 2010 at that site DSH-10. And I'll just go back for 1 minute. I wanted to point out that DSH-10 is actually physically closest to the Deepwater Horizon wellhead. The Nancy Foster samples were collected right here. And then DSH-08 is a little bit farther away. So here's a depth profile. And each of these lines corresponds to an excitation emission pair. So the black and the gray are those two peaks for naphthalene. And you can clearly see we've got a bump at the surface, we've got one at about 400 meters, and we've got another one down at about 1,400 meters. And these EAMs, again, were done in the COBA lab. This one is the surface profile, and you can see that strong oil peak there. This one is from 400 meters. This one is at 1,000 meters, which would be right here, where you don't have an awful lot of fluorescence going on at all. I'll point out the difference in scale. 12 quinine sulfate equivalent units, 16, and here it's 4. So this is a typical CDOM profile, and you can see that clearly from the shape as well as the intensity. So now moving on to the samples that I did. So I'm going to give you the really condensed, here's what I took away from all of this. These are the 3 different cruises at the naphthalene peak, so that all of the other excitation emission is gone. We're just going to take a look at what those water samples look like over the course of time. The earliest samples from December are this blue line, and you can see we've got a peak at the top, which is about 3 quinine sulfate units. February, it's a little bit higher at the surface, but here's something interesting. At about that was about 50 meters, we've got a peak in the subsurface. And then it drops down, still a little hint of that subsurface plume. And surprisingly, in May, it's going down at the surface and at 50 meters, but look at the subsurface. And from what I understand, many people were saying that the oil was gone from the water column within months of the capping of the wellhead. Well, this was May 2011, and it doesn't look like it's gone. It's not terribly high, 2 quinine sulfate equivalent units, but has the possibility to be toxic for the environment. This is just zooming in so that you can see with a little bit better visual how that 55-meter sample separated from the rest of the series, and that's the EAM from 55 meters. So you can clearly see that double peak of naphthalene there, and we know that that's an oil signature. These shaded areas here are the first and second order Raman and Rayleigh. That's why they're masked, because the intensity is just overwhelming all of the signal. So now let's take a look at DSH-10, which again is a little closer to the wellhead. First is the blue. Second, in February, is the green, where we see the presence of the oil actually increasing at the surface. And again, in May, we've got more oil present at the surface in May, when many people were saying it was gone. So this is just zooming in a little bit so you can see how there clearly is the presence of different subsurface behavior that's going on over the course of the evolution of that year. This is an EAM from 75 meters on the February cruise, and I just wanted to point out that this is much more characteristic of normal marine organic matter. This is a protein-like signature. You don't see the same intensity that you do with the oil, and the excitation emission is shifted slightly lower. So this might be an indication of the microbial response to the oil that was in the water column. So my conclusions from the field sampling is that we still had oil through May 2011, which was kind of surprising when I went back and looked at those samples. I can confirm that because of the further work that I did at the wave tank and in the baffle flask experiments. We saw at DSH-08 that deep water plume at 1,100 meters that we confirmed with fluorescence, and we saw it come back in May 2011. what was going on. Some people have proposed that it was a resuspension of material in the benthos, but I came across an article by Collian and colleagues that suggests that the Deepwater Horizon wellhead was still leaking through May 2012 through samples that were collected and showed no signs of weathering. So that would bear some investigation. The fluorescence of the Deepwater plume was the highest at DSH-10, which was closest to the wellhead, in February, not in December. So is that resuspension of sediments, or is that continued leaking? So I just wanted to give some background to why do we care? Why do we care about this, continued presence of petroleum? And we have an awful lot of biological studies that are showing the after effects through reduced reproductive strength in dolphins particularly, but in other organisms, birds, sea turtles, strandings and deaths, and hard corals dying from the fallout of the Deepwater Horizon plume. And yes, a lot of that might just be from smothering, but it's possible that the toxicity, even at the low parts per billion range, could have a lasting effect on the deep sea. And we've got all of these wells out there in the Gulf of Mexico. They're not all active wells, but any and all of them are capable of leaking. For example, the Taylor Energy well, which now has been projected to surpass quantity-wise the amount of oil that was released in the Deepwater Horizon. We've also got oil that comes from transportation. This figure is from Deep Sea Oil in the Sea 3, and just shows the amount of transportation-related oil spills that are also impacting the Gulf of Mexico, as well as around the world. So my overall conclusions from all of this is that fluorescence is easy, it's fast, it doesn't take an awful lot of expensive equipment, it doesn't take an awful lot of dangerous chemicals, which are difficult to take to sea. The fluorescence intensity as well as that spectral shape are affected by the dispersant to oil ratio, so that can be used by responders. The EAMs from the water samples that were collected in August 2010, were similar to the ones that we saw in the wave tank at the time of 45 minutes after the input of the oil. So we can say for sure that fluorescence is related to chemistry because we did the chemistry at the Bedford Institute of Oceanography. And finally, I found that continued presence of petroleum in the water column. So what will we do with this? What will anyone do with this? What can I do with this? We need to look at the range of response. I started digging into it with those 25 types of oil, but there's room for a lot more work as far as determining how different viscosities of oil respond, especially fuel oils. Fuel oils are very complex mixtures, and as you saw in the transportation graphic, that is responsible for a large amount of input to the environment. Could we develop laser optic sources that could get down deeper into the UV? As I mentioned, the xenon lamps are, they're very good, but they don't get down into the deep UV as well as a laser source might be able to do. Then we could put that on a CTD and do much better profiling while we're collecting our discrete water samples. It would be great to develop a set of crude oil standards so that we could put things into crude oil units instead of quinine sulfate equivalents or Raman units and be able to say this is equivalent to this parts per billion of oil. And I would like to argue that we should be out there monitoring and doing depth profiles continually. Because of all those wells out there, we need to know what the background is. We didn't really have a good idea, especially given that there are all the natural seeps present in the Gulf of Mexico. When will we be back to normal? We just didn't really know. So we should continue doing that. So In closing, I'd like to thank the captain and crew of the Weatherbird, the staff at Cougar, Paula and Anna. Let me take a drink. As Paula said, there'll be tears. These are all the agencies that provided funding and my family. All of the references I used in this presentation and questions I'd be glad to answer. Anyone? Yes.